All right, now that we understand the basic procedure for finding extreme values, let's look at a more interesting function. Our function is x cubed minus 8 to the 2/3 power on the interval minus 2 to 3. Part A is the same as it was last time. We want to find the local extrema. So what rule should we be using for this? And as usual, feel free to pause the recording and try to do the problem on your own and then watch and see if you got it right. We're going to need the chain rule, right? Because we have one function inside of another. So we've got something to the 2/3 power. So that becomes 2/3 the same function, remember, in the chain rule, to the negative 1/3. And then the chain rule says you're not done yet. You got to take the derivative of the inside function, which gives us a 3x squared. We can cancel these 3's. And we're supposed to define the critical points, which is where the derivative is 0 or undefined. Is this derivative ever undefined? Think carefully. Is this derivative ever undefined? We've got a negative exponent, which should make us concerned, or at least curious. So what does it mean to have a negative exponent? That means that this is really a way of thinking about that is on the bottom of the fraction. So I've got a 2x squared on the top, and on the bottom I've got x cubed minus 8 to the 1/3 power, right? So actually this is undefined because the denominator can be 0 when x is what? When x cubed is 8 or when x is 2. So f prime of x is undefined at x equals 2. So this is why I wanted to do this example, so that we would see one where the derivative is undefined. And let's see why, if the derivative undefined because the actual original graph is undefined. Because we know that if f has something funny happening, like a discontinuity or a vertical asymptote or a hole, then we know that f prime doesn't have any chance of existing. But at x equals 2, nothing unusual happens, right? I get 2 cubed, which is 8, minus 8, I get 0. And 0 to the 2/3 power, that's 0 to a positive power. That's just 0. So in fact, nothing strange is happening to the function f, but the derivative is undefined at 2. And now where is the derivative 0? If I set this equal to 0, if we want a fraction to be 0, what part of the fraction has to be 0, the top or the bottom? It's the top, right? So this means that 2x squared is 0, which means that x equals 0. So those are our two critical points. We're going to want to put those on our number line. 0 and 2. And now we want to be testing values on either side by plugging into f prime. And so keep track. If you think back to the last problem, there were times when you plugged into f prime, there were times when you plugged into f double prime, times when you plugged into f. So let's try to think in advance of what we should be plugging into in each of the upcoming parts of this problem. Here we're trying to find local extrema, so I need to pick a number over here like -1 and plug into f prime. So the sign of f prime of -1 is, so now I've got a fraction, that's fine. The top of it is going to be positive. And on the bottom, if I plug in -1, I get -1 cubed, which is -1 minus 9. This is saying taking the cube root of a negative number. And if you take the cube root of a negative number, you get a negative number, right? Like the cube root of -27 is -3. So I've got a positive over a negative, which will be negative. So f is decreasing there. So 0 might be a local what? Might be a local min, definitely not a local max. We need a number in here. So let's take the sign of f prime of 1. The numerator still can't be negative. The denominator, 1 cubed minus 8, is still a negative number, right? This is -7, and the cube root of -7 is still going to be a negative number. So I again got a positive over a negative. So that means x equals 0 ended up being neither a max nor a min. Let's pick a number out here. Our domain goes all the way over to 3, so let's pick 3. Again, something squared can't be negative, so we get a positive on the top of the fraction. And now on the bottom, when we get 3 cubed, we get 27. 27 minus 8 is a positive number, and the cube root of a positive number will be a positive number. So now we got a positive, so now f increased for the first time starting at x equals 2. So what's the conclusion? So f has a local minimum at x equals 2 and has neither max nor minimum, neither max nor min at x equals 0. So start thinking to yourself what it might be happening at x equals 2. We know that the derivative doesn't exist. We know that 2 is a local minimum. Start trying to picture in your head what the graph might look like at 2. That's going to be what we get to at the very end of this problem. Okay, part B. Let's find the x values of the global extrema. So we're just following the same parts as in the previous problem, except there's going to be one final part D here where we sketch the graph of f so that we can see what interesting thing was happening at x equals 2. So again, here we really already know something from our number line because the graph is going down, leveling off, going down some more, and then going up, right? So we know we're going to have a global min at x equals 2. The question is whether the global max is going to be at this endpoint or at this endpoint. So we're going to have to see whether the function is higher at the left endpoint or the right endpoint. So what should we be plugging into now? F, f prime, or f double prime? We want to be comparing the y values of the original graph, the original function, so we want to be plugging into f. So we want to compare f of the leftmost endpoint, which is negative 2, f of our local extremum, which was 2. Even though we know that's already going to be, we already know that's going to be the global min, we're going to write it up here just for the sake of completeness to get into good habits, and then f of 3. So if I plug in negative 2 cubed minus 8, that's negative 16. Negative 16 to the 2/3 power. Are we allowed to take the 2/3 power of a negative number? What do you think? We are. Because this is like saying negative 16 squared, which is 256, and then taking the cube root of that. So this is the cube root of 256. F of 2 is nice and easy, because f of 2 we get 2 cubed, which is 8, minus 8, which is 0. So that's just 0. And f of 3 we get 3 cubed minus 8, which is 19 to the 2/3. And if you want to compare these, you could rewrite that as 19 squared. 19 squared is 361. Cube root of that. Of course, you have your calculators as well, so you're free to do that. So we were trying to figure out which endpoint was higher at x equals negative 2 or at x equals positive 3. And by comparing these two y values of f, we see that this is where we're going to have our global maximum. Thus, f has a global minimum right where we thought it was going to be at x equals 2, and a global maximum at one of the endpoints, and in this case, it was at x equals 3. Alrighty. Ready for the inflection points? We want to find the inflection points. Remember, we've got our formula for f prime of x. Inflection points, we're going to need to look at f double prime. So it's a matter of preference which formula you want to use for f prime to compute f double prime. If you write it as a fraction, you got to use the quotient rule. If you write it as a product, you got to use the product rule. So I'm going to go for the product rule. If you want to do it as a quotient, you'll get the same answer in the end. So that's how I'm going to rewrite f prime. So I just took the first line of f prime from the previous chalkboard, canceled the 3's, and put the x squared out front. So we've got a product rule happening here to get f double prime. Derivative 2x squared is 4x, and then we leave the other piece alone. Then we leave the 2x squared alone, and we take the derivative of this x cubed minus 8 to the negative 1/3. And what rule are we going to need for that? We've got one function inside of another function, which always tells us chain rule. So the negative 1/3 comes down. We get x cubed minus 8 to the negative 4/3 now. And then the chain rule says, you're not done yet. Take the derivative of x cubed, which is 3x squared. Lovely. I told you this would be more interesting. OK, let's see if we can write this in a cleaner way. This is 4x over x cubed minus 8 to the 1/3. Here these 3's cancel. We've got a negative 2x squared times x squared. So negative 2x to the 4th over x cubed minus 8 to the 4/3. You might be doing this some completely different way. That's fine. I've got one fraction minus another fraction. What do we need to make that happen? Common denominator. This is to the 4/3 power. This is the same thing to the 1/3 power. So the common denominator actually is this, meaning we want to multiply this by x cubed minus 8 over x cubed minus 8. Because x cubed minus 8 is x cubed minus 8 to the first power. And when I multiply by x cubed minus 8 to the first power, I add 1 to this. 1/3 plus 1 is 4/3. So we're going to get 4x times x cubed minus 8 to the first power minus this other numerator all over x cubed minus 8 to the 4/3 power. And then we can simplify this numerator a little bit more. Let's just remind ourselves of what it is we're computing, f double prime. If I multiply this out, I get 4x to the 4th minus 2x to the 4th. So that's 2x to the 4th. And then this is 4x times negative 8. That's negative 32x all over x cubed minus 8 to the 4/3. And if we really want, we can simplify it even a little bit more by pulling a 2x out of the top. And we're left with x cubed minus 16 all over this. If you chose to do it with a quotient rule, your algebraic steps along the way might be a little different, but you should end up with the same thing. If not, you can check to see where you made a mistake. OK, we got to check where this is undefined and where this is 0. No surprise, it's still undefined at x equals 2, right? Because f prime itself was undefined at x equals 2, so there's no way that f double prime could possibly somehow magically be defined where its original function f prime wasn't undefined. Wasn't defined. Let me just say that more clearly. Since f prime was undefined at 2, f double prime must be undefined at 2. So f double prime is undefined at 2. Let's keep that in mind. And now we want to set this equal to 0. Setting a fraction equal to 0, as we just discussed, means that the numerator is 0. So if we want to set this equal to 0, that means that 2x times x cubed minus 16 is 0. Well, we're back in our favorite situation where you have the product of real numbers being 0. One of them's got to be 0. So if 2x is 0, or x cubed minus 16 is 0, 2x is 0 means x is 0. X cubed minus 16 is 0 means x is the cube root of 16. So we've got how many different things to put on our number line for f double prime? We've got 3. 2 places where f double prime is 0, 1 where f double prime is undefined. Well, certainly 0 is to the left. And then which comes next? 2 or the cube root of 16? 2 is the cube root of 8, so the cube root of 8 is less than the cube root of 16. So I'm going to put a 2 here and a cube root of 16 here. And now we've got to check some signs here, right? So let's notice the bottom. The bottom is something, a cube root, but then raised to the 4th power, right? So when I take the cube root, I might get a positive or a negative, right? Raising something to the 1/3 power is taking a cube root. But if I get a positive or a negative and then I raise it to the 4th power, what do I always get? We always get a positive. So this thing here is always going to be positive, no matter what. So all we really have to do is check the sign of the top. So let's pick a number to the left of 0, say -1. So f double prime of -1. Oops, I mean to say the sign of f double prime of -1, right? The sign of f double prime of -1. Two times a -1 will be a negative. -1 cubed minus 16 will be a negative. And you told me the denominator is always positive. I mean, I heard you telling me that. I hope you said that. So we get positive over positive, which is positive. So what does that tell us about the concavity of f out there? We are concave up. Let's pick a number in here, like 1. So the sign of f double prime of 1. 2 times 1 is positive. One cubed minus 16 is negative. Denominator is always positive. So we get a negative over a positive, which is a negative. So we did find an inflection point at 0 because we changed concavity there. Remember, 2 is the place where we're really interested in what's happening here. 2 is where the derivative was undefined, but the original function was defined. So we've been asking you to think in your head what the graph might look like at x equals 2. You're about to get a big hint right now. We need to pick a number in here. 2 is the cube root of 8. This is the cube root of 16. Let's pick the cube root of, oh, I don't know, sine of cube root of 11. Well, 2 times the cube root of 11 is positive. If I take the cube root of 11 and I cube it, I get 11. 11 minus 16 is negative. And the denominator is always positive. So we get a negative over a positive, which is a negative. So we're concave down on both sides of 2. And 2 was a local minimum. Think to yourself now, what must that graph look like? Part D, we're going to sketch it. OK, we ran out of a little bit of room there, so let's move over to here and pick one more point. The sine of f double prime of, what is our rightmost endpoint? 3, I believe. 2 times 3 is positive. 3 cubed is 27 minus 16. That's another positive. The denominator is always positive, so that's positive, so we're concave up. Whew. We told you that was going to be a little bit more involved algebra. So let's our conclusion here. F has inflection points where? Inflection points. Well, we were concave up until 0 and concave down on the other side. So one is at x equals 0. Not at x equals 2 because we were concave down on both sides. But then we did change concavity again at the cube root of 16. And at x equals cube root of 16. All right, we're ready for our last piece here. Sketch f of x. So how about pause the recording and give it a try to sketch it on your own before we do it all together here. And pay particular attention to what's happening at x equals 2. All right, I'm ready to sketch it. So we knew that we had a global minimum at x equals 2, and the y value there was 0. So we know that the graph comes down and touches the x-axis at x equals 2. What are the other interesting points? X equals 0 was a critical point from part A, and we have an inflection point at the cube root of 16, which is somewhere over here. So now we need to combine. You have to look back to your number line from part A. From part A, it says we are decreasing coming from over here, and from part B, part C, we are concave up. So what does decreasing concave up look like? It looks like this. And this actually is a perfectly horizontal slope right here at x equals 0. If you look back to part A, you found that f prime of 0 was 0. So the slope levels off perfectly there. But now look back to your number line from part A, and you see that f prime becomes negative, so f keeps decreasing here, except that we change to concave down. So until x equals 2, according to part B, we're decreasing, and according to part C, we're concave down. So what does decreasing concave down look like? It looks like that. So we're about to figure out, to see graphically, what happened at x equals 2. Because now, according to part B, f starts increasing, but according to part C, we're still concave down. So what does increasing concave down look like? It looks like this. So we hit the x-axis and we bounce right off it, like that. And here's our cube root of 16. And after cube root of 16, we're supposed to be concave up. And that's where we end at positive 3. And this is where we started at x equals negative 2. So the reason that f prime was undefined at x equals 2, even though f was defined at x equals 2, was that we had this, what's called a cusp. The graph came down, got a vertical tangent, and then bounced off again with another vertical tangent. So it's similar to the absolute value graph, where the derivative doesn't exist at that point, but in a different way. Here we're coming in, and this is called a cusp, whereas what people often call the absolute value graph is they call that a corner. That's not the official math name. There is really no official math name. But it is a place where the derivative doesn't exist. The function, remember our old word, the function is not differentiable at x equals 2. But it really took all of this math, the second derivative, the concavity, to figure out why it was that f prime of 2 was not defined. All right. Did you enjoy that? We now have a check your understanding. That is the end of our week's work. So please go ahead and do that check your understanding, and we'll see you back here next week.